July 26, 1944. Tinian Island, Mariana Chain, Pacific Ocean. The island shudders under the weight of American bulldozers. Marine Captain Robert Johnson stands on the captured Japanese airfield at Ushi Point, watching as the first Seabees arrive in their jungle green fatigues, tropical baseball caps lifted against the heat. Behind him, Japanese positions still smoulder from yesterday's napalm strikes. Around him, scattered across the coral runway, lie the twisted remains of Nakajima reconnaissance aircraft, some relatively intact inside hangars, others blown apart by naval bombardment. The fighting officially ended just hours ago. Japanese soldiers still hide in caves throughout the southern limestone ridges, and yet, impossibly, construction has already begun. Johnson watches as teams of Seabees swarm across the 4,380-foot Japanese runway, assessing damage, marking sections for repair, establishing supply dumps. Heavy equipment rumbles off landing craft before the beach is fully secured. Within 6 hours of the island being declared secure, surveying teams mark out expansion plans that will transform this modest airstrip into something unprecedented. Within 45 days, this same location will become North Field, featuring multiple 8,500-foot runways capable of launching hundreds of B-29 superfortresses against Japan's home islands. Within 2 months, 6 complete runways will operate simultaneously from this 39-square-mile coral island, making Tinian the largest airbase in the world. The mathematics appear impossible. 6 8,500-foot runways, each 500 feet wide. 13 miles of taxiways at North Field alone. Housing for 40,000 personnel. Fuel storage for millions of gallons. Ammunition magazines by the hundreds. Hospitals capable of treating thousands. All on an island that possessed no natural harbour, no infrastructure, no existing construction materials beyond coral and jungle. All while Japanese artillery still fires from the southern caves. All in less time than traditional contractors required to complete a single runway in peacetime. What Captain Johnson witnesses represents the beginning of construction achievement that defies conventional understanding of engineering, logistics, and industrial capability. The Naval Construction Battalions, soon to be universally known as Seabees, arrived in the Pacific with neither precedent nor adequate preparation. They created, from absolute zero, the physical infrastructure that enabled American power projection across 6,000 miles of ocean. They built bases on islands that appeared on no accurate maps. They constructed ports where coral reefs made anchorage impossible. They transformed jungle into operational air bases faster than anyone thought possible. And they accomplished this through innovations in prefabrication, standardization, and construction technique that revolutionized military engineering while establishing principles that influence industrial construction decades later. The story begins not with victory, but with catastrophic surprise, with burning ships and desperate improvisation, with the recognition that civilian contractors cannot operate in combat zones, and that traditional military construction doctrine cannot support offensive operations across the world's largest ocean. December 7th, 1941. Pearl Harbor, territory of Hawaii. The Japanese attack destroys or damages 8 battleships, 3 cruisers, 3 destroyers, and 188 aircraft. More critically for future Pacific operations, the attack reveals the fundamental vulnerability of American forward-basing strategy. Civilian contractors, employed throughout 1940 and 1941 to construct advanced bases across Pacific islands, cannot legally resist military attack under international law. Resistance means summary execution as guerrillas. Every American construction worker on forward Pacific islands represents a liability rather than an asset once hostilities commence. The United States Navy faces simultaneous requirements that appear mutually exclusive. Offensive operations against Japan demand advanced bases throughout the Pacific. Bases require extensive construction. Construction requires skilled labor, but skilled civilian labor cannot operate in combat zones. On December 28, 1941, just 21 days after Pearl Harbor, Rear Admiral Ben Muriel, Chief of the Bureau of Yards and Docks, requests specific authority to activate, organize, and man naval construction battalions. These units will combine construction expertise with military discipline, allowing them to build under fire and defend what they build. On January 5, 1942, the Bureau of Navigation grants authorization. On March 5, 1942, all construction battalion personnel receive official designation as Seabees, derived from the initials CB for Construction Battalion. Admiral Muriel personally provides their motto, Construimus Batuimus, we build, we fight. The organizational structure represents radical departure from military tradition. Standard naval regulations restrict command of naval personnel to line officers of the fleet. But construction battalions require leadership from Civil Engineer Corps officers trained in construction skills rather than naval operations. The Bureau of Naval Personnel strenuously objects to granting command authority to CEC officers. Admiral Muriel personally presents the issue to the Secretary of the Navy. On March 19, 1942, after deliberation, the Secretary grants CEC officers military authority over all officers and enlisted men assigned to construction units. This decision, incorporated into Navy regulations, removes the major administrative roadblock preventing Seabee operations. Recruitment targets skilled tradesmen rather than raw recruits. Navy recruiters focus on men who helped build Boulder Dam, the national highways, and New York's skyscrapers. To obtain these experienced workers, military age requirements are waived to age 50. Several men past 60 successfully enlist despite regulations. Men receive advanced rank and pay based on experience, making Seabees the highest paid group in the United States military. The first 60 battalions average 37 years of age. These are master carpenters, electricians, heavy equipment operators, welders, plumbers, surveyors, draftsmen, and engineers. They know more than 60 skilled trades. They represent the industrial expertise of American civilian construction concentrated into military units. In December 1942, President Franklin Roosevelt orders voluntary Seabee enlistments ceased. All future personnel come from the selective service system, significantly lowering average age and reducing the concentration of skilled workers. But the first-generation Seabees, those who deploy in 1942 and 1943, bring expertise that cannot be taught in boot camp. Their knowledge, passed to younger recruits through on-the-job training in combat conditions, becomes the foundation of Seabee capability. Training occurs at newly established naval construction training centers, named for former Civil Engineer Corps chiefs, Camp Endicott at Davisville, Rhode Island, camps named for Admirals Rousseau, Holiday, Park, and Peary. The training is brief but intense. After Navy boot camp, Seabees attend weapons training with the Marine Corps, then short Navy combat engineering schools. The Marines teach them to fight. The Navy teaches them to build under fire. Then they ship out, most to the South Pacific, where conditions await that no training can fully prepare them for. February 17th, 1942. Bora Bora, Society Islands. The 1st Naval Construction Battalion Detachment, later redesignated as the Bobcats, becomes the first Seabee unit to deploy overseas. They arrive just 296 men strong, tasked with constructing a fuel depot on the southern route to Australia. They encounter conditions that become harbingers of what awaits Seabees elsewhere. Incessant rain transforms work sites into swamps. Multiple types of dysentery strike the unit simultaneously. Numerous skin diseases, some unidentified, afflict workers exposed to tropical vegetation. Elephantiasis, transmitted by mosquitoes, remains an ever-present threat. Combined, these conditions make work miserable and reduce efficiency dramatically. But the Bobcats succeed. Their fuel depot provides critical support to Task Force 44 during the Battle of the Coral Sea in May 1942, demonstrating that American power projection depends on constructed infrastructure, not just combat vessels. The pattern establishes itself immediately. Where Seabees build, American forces operate. Where construction fails, operations fail. The Pacific War becomes fundamentally a construction competition. Can America build bases faster than Japan can defend islands? Can Seabees transform captured territory into operational platforms before Japanese counterattacks eliminate bridgeheads? Can the United States project industrial capability across 6,000 miles of ocean faster than Japan can reinforce interior defensive lines? The answer emerges through innovation rather than traditional engineering. Seabees do not build to peacetime standards. They build to operational requirements under combat conditions, using whatever materials and methods work fastest. This philosophy produces breakthrough developments in prefabrication, standardization, and rapid assembly that fundamentally alter construction practice. The Quonset hut exemplifies Seabee innovation through simplicity. The structure represents pure functional design, stripped of all unnecessary complexity. In 1941, the United States Navy approaches the George A. Fuller Construction Company with specific requirements. The Navy needs an all-purpose, lightweight building that can be shipped anywhere and assembled without skilled labor. The structure must withstand tropical heat, Arctic cold, and Pacific typhoons. It must provide weather protection for personnel, equipment, and supplies. It must be assembled quickly by small crews using only hand tools. And it must be manufactured in enormous quantities, using materials that don't compete with aircraft production. The George A. Fuller Company delivers the first prototype within 60 days of signing the contract. The design draws inspiration from the British Nissen hut used in World War I, but incorporates critical American improvements. The Quonset hut employs a self-supporting arch structure made from galvanized corrugated steel sheets attached to T-shaped steel ribs. The semicircular design distributes structural loads evenly, requiring no internal supports and creating completely unobstructed interior space. The arch shape sheds rain and snow effectively while resisting wind forces. The standardized design allows mass production using industrial manufacturing techniques. The original Quonset hut measures 16 feet wide by 36 feet long with an 8-foot radius, providing 576 square feet of floor space. The structure can be erected by 8 men in one day using only hand tools. Each component ships as a standardized unit. The steel panels lock together with hooks and slots. The end walls, typically plywood, attached to pre-drilled frames. No specialized construction knowledge is required. If workers can read assembly diagrams and operate wrenches, they can build Quonset huts. The Navy quickly standardizes dimensions. The T-rib Quonset, first production version, measures 16 feet by 36 feet and weighs approximately 2.5 tons. The Quonset redesign, incorporating feedback from field operations, measures 20 feet by 48 feet and weighs 3.5 tons, providing 960 square feet of floor space. The Quonset 40, nicknamed the Elephant Hut, stands 40 feet wide by 100 feet long, suitable for warehouses and maintenance facilities. Between 150,000 and 170,000 Quonset huts are manufactured during World War II. By war's end, approximately 120,000 strand steel huts, an improved version using different steel specifications, supplement Fuller production. The implications extend beyond simple shelter. Quonset huts provide 86 official designated uses and countless unofficial applications. They serve as barracks, mess halls, hospitals, maintenance shops, supply warehouses, command centers, recreation facilities, chapels, and bakeries. They house radar equipment, communications gear, ammunition, fuel, food, and every other material required for military operations. They can be assembled on concrete foundations, wooden pilings, or directly on coral or permafrost. They ship efficiently, with 375 square feet of runway equivalent surface standing just 28 inches high when bundled. 2 men can carry a single steel panel at a run. On Tinian, Seabees construct thousands of Quonset huts in weeks. The 6th Naval Construction Brigade, comprising eventually the 29th, 30th, and 49th Naval Construction Regiments, builds housing for more than 12,000 Seabees, 13,000 other naval personnel, and 21,500 Army personnel. Each camp requires hundreds of huts for berthing, sanitation facilities, mess halls, and administrative spaces. The prefabricated standardization allows crews to work simultaneously on multiple structures. As soon as foundations are prepared, huts rise in assembly line fashion. Sites that required months of construction using traditional methods become operational in weeks using Quonset technology. But huts alone do not create air bases. Runways determine operational capability. And in the Pacific, where islands offer coral, jungle, and mud but rarely concrete, runway construction presents challenges that threaten to strangle offensive operations before they begin. The problem manifests brutally simple. B-29. Superfortresses require runways at least 8,500 feet long and 500 feet wide to operate safely with full bomb loads. Each fully loaded B-29 weighs 140,000 pounds at takeoff. Traditional concrete runways require months to construct, consume enormous quantities of cement that must be shipped across thousands of miles, and cannot be modified or repaired quickly when damaged by bombing. Coral runways, crushed and rolled, work initially but deteriorate under heavy use, especially during tropical rains. Mud becomes the operational enemy, grounding aircraft and transforming airbases into useless swamps. The solution arrives through elegant engineering developed by the Army Corps of Engineers at Waterways Experiment Station in Mississippi. In November 1941, 1 month before Pearl Harbor, the 21st Engineers construct a 3,000-foot experimental runway at Camp Mackle near Marston, North Carolina, using 18 railroad carloads of a new material, pierced steel planking. The runway takes 11 days to construct, but demonstrates revolutionary capability. Aircraft operate on virgin ground without concrete or extensive preparation. General Henry Arnold of the Army Air Corps calls it the year's greatest achievement in aviation warfare, not referring to the massive Carolina maneuvers exercises, but specifically to the Marston strip runway that enables them. The material receives official designation as pierced steel planking, or PSP, but becomes universally known as Marston Mat, named for the North Carolina town where initial production occurs. Each standardized plank measures 10 feet long by 15 inches wide, constructed from 10-gauge low-carbon steel. The steel is cold rolled to create longitudinal ribs for strength, then pierced with 87 holes arranged in 3 rows across 29 positions along its length. The holes serve multiple functions. They reduce weight by 17.5% compared to solid steel, bringing each plank to 66 pounds. They provide drainage, preventing water accumulation that would undermine the runway. They improve aircraft tire traction. The edges of each hole are flanged, increasing structural strength and helping lock planks in position. The manufacturing process involves 5 steps. First, longitudinal ribs are pressed into blank steel sheets. Second, slots and hooks are punched out along the edges. Third, the 87 holes are punched and flanged. Fourth, hooks are bent 90 degrees to allow planks to interlock. Fifth, planks are cleaned, degreased, and painted. By December 1941, 2 factories produce 4 million square feet of Marston mat. A year later, 29 factories operate at full capacity. By January 1944, more than 180 million square feet ship overseas, enough for 240 runways measuring 150 by 5,000 feet. By war's end, nearly 2 million tons of Marston mat are produced, representing enough steel to build 600 Liberty ships. The installation technique is straightforward, but labor-intensive. Workers first clear and level the site. On Pacific islands, this typically means bulldozing jungle, then rolling crushed coral into a flat surface. The coral provides a stable base that drains well. Workers lay the first course of Marston mat with hooks facing one direction. The second course interlocks with hooks facing the opposite direction. This pattern continues across the width of the runway. To facilitate damage repair, alternating courses with reversed hook directions allow individual planks to be removed by two men using pry bars. Damaged sections can be replaced in minutes rather than hours. The operational advantages prove decisive. A 3,000-foot runway requires just 1,200 tons of Marston mat and can be laid by 100 workers in less than 100 hours. Navy Seabees reduce this time dramatically through experience and refined techniques. In the Pacific Theatre, Seabees construct a 5,000-foot long by 200-foot wide runway in 2 days when necessary. The mat can be laid over crushed coral, palm fronds, loose straw, or virtually any surface that provides basic leveling. The sandwich of steel and vegetation absorbs moisture and eliminates dust that would otherwise shorten engine life and create operational hazards. At Tinian, the scale of Marston mat deployment exceeds anything previously attempted. The 15,000 Seabees of the 6th Naval Construction Brigade face unprecedented requirements: 6 complete runways, 4 at Northfield, and 2 at Westfield. Each runway measures between 425 and 500 feet wide and 8,500 feet long. 13 miles of taxiways at Northfield alone require additional matting. Parking hardstands for hundreds of B-29s demand still more. The total Marston mat requirement exceeds several million square feet. The Seabees adapt techniques to island conditions. Sharp coral, while providing excellent drainage, damages tires on construction equipment and punctures workers' shoes. Maintenance crews work continuously to repair bulldozers, shovels, trucks, and other machinery damaged by coral abrasion. Equipment operates 20 hours daily, with 4-hour maintenance windows preventing complete breakdown. In characteristic Seabee innovation, one construction crew has marine tank teams fire armor-piercing shells into hillsides, creating holes for dynamite charges that blast coral more efficiently than conventional excavation. The Seabees blast, haul, and pack enough coral to fill 3 times the volume of Hoover Dam. They operate asphalt plants to pave taxiways. They construct the assembly buildings where atomic bomb components will later be united. They build every support structure required for the largest airbase in the world. And they complete every runway on time. None requires more than 53 days from initial clearing to operational status. Most are completed faster, including the primary Northfield runways finished in 45 days. The comparison to Japanese construction capabilities reveals the magnitude of American advantage. Japanese engineers, working on Tinian before American invasion, spent more than 2 years developing 3 modest airfields. The longest Japanese runway measured just 4,700 feet. Japanese construction employed impressed Korean labor and Japanese military engineers using traditional methods, hand tools, and minimal mechanization. When American forces capture Tinian, they find extensive defensive fortifications, but minimal developed infrastructure. Japanese bases cannot support long-range bomber operations because Japanese engineering philosophy prioritizes defensive positions over offensive capability. Seabee construction inverts this philosophy entirely. Defensive positions receive minimal attention. Operational requirements drive every decision. If runways enable B-29 operations, runways receive priority regardless of vulnerability. If housing can be built from prefabricated components in hours, elaborate defensive fortifications that require weeks are abandoned. The Seabees accept that bases under construction remain vulnerable to attack. They plan for damage repair rather than damage prevention. This approach, radical compared to traditional military engineering, allows Seabees to construct faster than enemies can destroy. The differential between Japanese and American construction capability extends beyond speed to scale and standardization. Japanese bases remain custom designed, built to local conditions using available materials. No two Japanese air bases employ identical designs. Equipment and structures from one base cannot be transferred to another. Supply chains remain complex and fragmented. American bases, by contrast, employ standardized components manufactured in the United States and shipped complete to forward areas. Quonset huts built in Rhode Island function identically on Tinian, Guadalcanal, or Iwo Jima. Marston mat panels made in 29 different factories interlock seamlessly. This standardization creates interchangeable logistics. Supply officers need not track unique requirements for individual bases. They order standardized units in standardized quantities using standardized shipping. The mathematics of this system reveal its power. The United States produces 170,000 Quonset huts during the war. If each hut provides 960 square feet of space and requires 3.5 tons of steel, total Quonset production represents 163,200,000 square feet of covered space using 595,000 tons of steel. Marston mat production reaches 2 million tons of steel for approximately 1,800,000,000 square feet of runway surface. Combined, American prefabricated construction materials for Pacific bases consume 2,595,000 tons of steel, enough to build more than 900 Liberty ships. Yet these materials create infrastructure supporting 400 bases across the Pacific, infrastructure that enables American forces to project power across 6,000 miles of ocean against an enemy fighting from interior defensive lines. The operational impact manifests dramatically. When American forces land on Tinian on July 24, 1944, the island possesses 3 damaged Japanese airfields, totaling approximately 12,700 feet of runway. By October 1944, just 68 days after the last Japanese resistance ends, Tinian operates 6 runways totaling 51,000 feet, with capacity for hundreds of B-29s. The first B-29 bombing missions against Tokyo launched from Tinian on November 24, 1944, just 4 months after American forces landed. This timeline compresses strategic transformation into operational immediacy. Islands progress from Japanese-controlled territory to operational American air bases in weeks rather than years. The logistics supporting Seabee operations reveal complexity that exceeds the construction work itself. Every nail, every gallon of fuel, every vehicle, every piece of equipment must travel from American factories to Pacific islands. The supply chain extends 6,000 miles across submarine-infested waters to coral atolls that possess no ports, no warehouses, no protection from weather. The system succeeds through methodical planning and massive redundancy that accepts significant waste as the price of ensuring critical materials arrive when needed. Consider the fuel requirements for Tinian construction. The 15,000 Seabees operate approximately 1,500 pieces of heavy equipment: bulldozers, graders, scrapers, rollers, dump trucks, cranes, pile drivers, concrete mixers, and asphalt plants. Each bulldozer consumes approximately 6 gallons of diesel per hour. Operating 12 hours daily, each bulldozer requires 72 gallons per day. 200 bulldozers require 14,400 gallons daily. Dump trucks consume 8 gallons per hour, requiring 96 gallons for 12-hour operations. 300 dump trucks require 28,800 gallons daily. Cranes and other specialized equipment add another 15,000 gallons daily. Total diesel fuel consumption exceeds 60,000 gallons per day for construction equipment alone. This fuel must be stored safely on an island, experiencing regular Japanese artillery attacks and occasional air raids. Seabees construct dispersed fuel farms using prefabricated steel tanks shipped from the United States. Each tank holds 10,000 gallons. 6 tanks provide 1 day of reserve. Prudent planning requires 15 days of fuel storage, meaning 90 tanks totaling 900,000 gallons. These tanks must be protected from artillery, camouflaged from air reconnaissance, and connected to distribution networks that deliver fuel to equipment across the island. Spare parts present even more complex logistics. A bulldozer operating in coral conditions requires track replacement every 300 hours. Tinian's 200 bulldozers operating 12 hours daily require track replacement every 25 days. Each track set weighs 2,000 pounds and costs $800. The island requires 8 track sets daily, 16,000 pounds of tracks, to maintain bulldozer operations. Over 45 days of intensive construction, track replacement consumes 360 sets, weighing 720,000 pounds, costing $288,000. These tracks must be manufactured in the United States, shipped across the Pacific, unloaded at Tinian, stored until needed, and installed by maintenance crews working around the clock. Hydraulic hoses fail regularly under the stress of continuous operations. Each piece of heavy equipment employs dozens of hoses. A single bulldozer uses 40 hydraulic hoses of various sizes. Failure of any single hose stops operations until replacement. Prudent maintenance requires spare hoses for every equipment type. The 1,500 pieces of equipment on Tinian require approximately 60,000 hydraulic hoses in inventory to prevent work stoppages from hose failures. These hoses must be protected from tropical deterioration, organized by size and type, and available immediately when failures occur. Tires represent another constant challenge. Heavy trucks operating on sharp coral experience flat tires daily. Each truck requires 6 tires. 300 trucks require 1,800 tires. Coral cuts tires so aggressively that replacement occurs every 200 hours of operation. At 12 hours daily, this means tire replacement every 17 days. The island requires approximately 100 tire replacements daily to maintain truck operations. Over 45 days, this consumes 4,500 tires, weighing approximately 675,000 pounds. These tires must be shipped, stored, and installed continuously. The personnel support infrastructure requires its own extensive logistics. 15,000 Seabees require 45,000 meals daily. Each meal requires approximately 2.5 pounds of food, totaling 112,500 pounds daily, or 5,062,500 pounds over 45 days. This food must be shipped refrigerated or preserved, stored in conditions preventing tropical spoilage, and prepared in field kitchens that themselves require equipment, fuel, and water. The refrigeration alone requires dedicated diesel generators consuming thousands of gallons of fuel daily. Water supply presents critical challenges. Men working in tropical heat require minimum 2 gallons per person daily for drinking alone. 15,000 men require 30,000 gallons daily just for drinking water. Hygiene, cooking, concrete mixing, and equipment cleaning require additional water. Total water consumption exceeds 100,000 gallons daily. Tinian's Japanese-developed well and reservoir system requires rehabilitation. Seabees sink 17 new wells, install pumps requiring fuel to operate, lay distribution pipes across the island, and construct storage tanks. The water system eventually provides capacity of 1,800,000 gallons daily, but achieving this requires weeks of work proceeding parallel to runway construction. Medical support requires infrastructure that many combat units lack. The 600-bed Base Hospital 19, constructed from modified Quonset huts, becomes operational in December 1944. Construction requires 60 Quonset 40 huts modified with additional floor space, electrical systems for surgical lights and diagnostic equipment, plumbing for sterilization and sanitation, and climate control to prevent tropical heat from killing patients. The hospital stocks medications, surgical supplies, diagnostic equipment, beds, linens, and food for patients. All of this must be shipped from the United States. The construction materials themselves overwhelm standard logistics. The 6 Tinian runways require approximately 40 million square feet of Marston mat, representing 110,000 tons of steel. This steel arrives aboard cargo ships, each carrying perhaps 5,000 tons maximum. 22 shiploads of Marston mat alone. The Quonset huts for 40,000 personnel require approximately 4,000 structures, representing 14,000 tons of steel components. Another 3 shiploads. The fuel tanks, ammunition magazines, warehouses, maintenance facilities, and administrative buildings require thousands of additional tons. Total steel requirements for Tinian construction exceed 150,000 tons delivered by 30 cargo ships over several months. These ships must be unloaded. Tinian possesses no deep-water port. Ships anchor offshore. Landing craft ferry cargo to beaches. Seabees construct temporary piers using pontoon causeways, essentially floating bridges that extend from shore to ships. The causeways themselves must be shipped from the United States as components, assembled offshore and anchored against currents, tides, and storms. A typhoon on July 28th damages pontoon causeways and interrupts unloading for 2 days. Seabees repair the damage and resume operations, but the incident reveals infrastructure vulnerability. Beach operations require specialized equipment and organization. Cranes lift cargo from landing craft. Trucks transport cargo inland to supply dumps. Seabees organize supply dumps by material type. Marston mat, Quonset components, fuel drums, spare parts, food, ammunition, and hundreds of other categories. Each dump requires guards against pilferage and sabotage, camouflage against air reconnaissance, and organization, allowing rapid retrieval. Men must be able to find specific items among thousands of tons of similar-looking crates and containers. The human cost of this achievement deserves recognition even beyond operational casualties. Seabees suffer from Japanese attacks, accidents, disease, and environmental hazards. Tropical diseases strike constantly. Malaria, dengue fever, dysentery, and numerous skin infections afflict workers. The heat in tropical islands proves debilitating. Men work in temperatures exceeding 100 degrees Fahrenheit, with near 100% humidity. Equipment failures cause injuries and deaths. Bulldozers overturn on steep terrain. Coral cutting equipment throws shrapnel. Dynamite charges detonate prematurely. Heavy construction materials crush workers when lifting equipment fails. During combat operations, Seabees work under fire. At Tinian, construction begins before the island is fully secured. Japanese artillery continues firing from southern caves throughout the initial construction period. Seabees dig foxholes along runways, jumping into them during bombardments, then emerging to continue work. At Guadalcanal, Japanese forces conduct nightly raids against Henderson Field, targeting both combat aircraft and the Seabees, maintaining and expanding the runway. At Iwo Jima and Okinawa, Seabees land with assault forces, suffering casualties alongside Marines while clearing beaches and establishing supply dumps. 200 Seabees are killed in combat. Another 2,000 receive Purple Hearts for wounds received in battle. These numbers understate total casualties. Disease, accidents, and environmental hazards kill additional hundreds. The nature of Seabee work makes precise casualty accounting difficult. Some Seabees serve temporarily with Marine units during assaults, their casualties recorded under Marine rather than Seabee designations. Some die from tropical diseases months after exposure, their deaths occurring in hospitals far from combat zones and recorded as medical rather than combat casualties. But Seabee casualties remain remarkably low considering the scale and danger of operations. More than 325,000 men serve as Seabees during World War II. The 200 combat deaths represent a casualty rate below 0.1%. This low rate reflects deliberate policy. The Navy values Seabee construction expertise too highly to employ them as combat infantry. Seabees receive weapons training and defend themselves when necessary, but their primary mission remains construction. When combat intensifies, Seabees withdraw to safer areas and resume work when fighting moves forward. This policy ensures that casualties do not eliminate irreplaceable construction capability. The relationship between Seabees and Marines deserves particular attention. Marines and Seabees develop mutual respect, born from shared hardship and complementary capabilities. Marines seize objectives. Seabees make objectives operational. At Tarawa, Marines fight for 3 brutal days to capture the island. Seabees land on day 2, working under fire to expand the airfield before the battle ends. At Saipan, the 18th and 121st Construction Battalions accompany assault waves, clearing beach obstacles and establishing supply routes while Marines engage Japanese defenders. At Iwo Jima, Seabees land on day 1, immediately beginning runway repairs on captured Japanese airfields while Marines push inland against savage resistance. Marines recognize that Seabee construction determines whether captured islands provide strategic value. A sign posted by the 3rd Marine Division, 2nd Raider Regiment on January 1, 1944, reads simply, "The Seabees never let us down." This tribute reflects operational reality. Marines can capture any objective if provided sufficient support, but captured objectives remain tactically useless until Seabees construct infrastructure. The relationship creates synergy, where Marine combat effectiveness depends on Seabee construction capability, and Seabee construction capability depends on Marine security. The scale of Seabee achievement across the Pacific exceeds comprehension through simple statistics. The Seabees, according to Navy official history, build housing for 1.5 million soldiers, sailors, airmen, and Marines. They construct tanks for storing 100 million gallons of gasoline. They build 700 square blocks of warehouses. They construct hospitals with capacity to treat 70,000 patients simultaneously. They build 111 major airstrips, 441 piers, and 2,558 ammunition magazines. These numbers represent physical structures. The human effort required to produce them across 6,000 miles of ocean under combat conditions cannot be quantified through statistics alone. Consider the logistics. Every Quonset hut component ships from American factories to Pacific Islands aboard cargo vessels. Every Marston mat panel makes the same journey. Every ton of construction equipment, every tool, every nail, every gallon of fuel for construction machinery, every pound of food for construction workers, all must be transported across the Pacific on ships that face submarine attack, storm, and the sheer distance that makes Pacific operations logistically nightmarish. Liberty ships provide the transportation infrastructure. These standardized cargo vessels, built by Henry Kaiser's shipyards at unprecedented speed, carry the materials of American construction capability. A single Liberty ship could transport enough Marston mat for a 3,000-foot runway in one cargo hold. It could carry sufficient Quonset hut components to build an entire camp. The integration of American industrial production, maritime transportation, and forward construction creates a system where Pacific Islands transition from enemy territory to American bases in timeframes that Japanese planners considered impossible. The Japanese perspective on American construction capability reveals the psychological impact of Seabee operations. Japanese intelligence officers observing American base development report findings that their superiors initially dismiss as impossible exaggeration. Reports describe entire air bases appearing in weeks on islands that possessed no infrastructure. Japanese reconnaissance aircraft photograph American bases under construction, revealing dozens of structures and extensive runway development proceeding simultaneously. Captured documents reference American construction units called Seabees that combine military organization with construction expertise, a concept that has no equivalent in Japanese military structure. Japanese engineering officers, examining Tinian after its capture, calculate that American construction on the island required approximately 15,000 workers operating for several months. This estimate proves accurate. What Japanese officers cannot comprehend is the methodology. Japanese construction doctrine employs large numbers of impressed laborers supervised by military engineers. Work proceeds sequentially. Foundations are completed before structures begin. Structures are completed before the next phase begins. American construction employs smaller numbers of skilled workers using prefabricated components and standardized techniques. Work proceeds in parallel. Multiple structures rise simultaneously. Construction adapts to materials rather than materials adapting to construction. Post-war interviews with Japanese officers reveal consistent themes. They express amazement at American construction speed. They describe American bases appearing almost overnight. They acknowledge that Japanese defensive planning could not account for American capability to make captured islands operational so quickly. Several officers note that American base construction invalidated Japanese strategic planning. The Japanese strategy of defense in depth assumed that American forces would require extended periods to develop each captured island into a useful base. This time would allow Japanese forces to regroup, reinforce, and prepare counterattacks. When American construction eliminated this timeline, Japanese defensive strategy collapsed. Islands captured in July launched offensive operations in October. Japanese forces found themselves defending against attacks launched from bases that should not yet exist. The technical comparison between Japanese and American engineering philosophy reveals fundamental differences in military-industrial capability. Japanese military construction prioritizes permanence over speed, defense over offense, craftsmanship over mass production. When Japanese engineers build an airfield, they excavate foundations to bedrock, pour concrete in multiple layers, allowing each to cure completely, install drainage systems designed for centuries of operation, and construct buildings meant to withstand typhoons and earthquakes. The resulting facilities are excellent quality, but require months or years to complete and employ materials that must be sourced locally, since Japanese logistics cannot transport massive quantities of construction materials across the Pacific. Japanese construction on Tinian illustrates their limitations. Colonel Kiyoshi Ogata's 50th Infantry Regiment spent more than 2 years developing Tinian's defences and infrastructure. The 3 airfields they built featured hand-cut coral runways crushed by steamrollers, the longest measuring 4,700 feet. Japanese engineers employed impressed Korean labourers working under military supervision using minimal mechanization. Construction proceeded through sequential stages. Site clearing occurred first, using hand tools and dynamite to remove jungle. Coral crushing followed, using small portable crushing equipment that processed perhaps 20 tons daily. Manual labour spread crushed coral, which steamrollers compacted. Each phase completed before the next phase began. The mathematics reveal the differential. Japanese engineers working for 2 years with several thousand labourers built 3 runways totaling approximately 12,700 feet. American Seabees, working 45 days with 15,000 men and 1,500 pieces of mechanized equipment, built 6 runways totaling 51,000 feet. Japanese construction rate, approximately 17 feet of runway per day. American construction rate, approximately 1,133 feet of runway per day. The American advantage, 66-1 in runway construction speed. This differential extends beyond simple speed to operational capability. Japanese runways barely accommodate their own medium bombers. The 4,700-foot maximum runway length restricts Japanese to aircraft like the Mitsubishi G4M Betty medium bomber, which requires 3,000 feet for takeoff with normal bomb load. The Japanese cannot base long-range heavy bombers on their runways, even if such aircraft existed in their inventory. American runways accommodate B-29 superfortresses that require 8,500 feet for takeoff with maximum bomb load. This capability difference makes American airbases strategic weapons, while Japanese airbases remain tactical facilities. Japanese officers observing American construction methods through intelligence reports struggle to comprehend the organizational principles. Reports describe American units arriving with pre-manufactured components that assemble rapidly. Japanese officers understand prefabrication intellectually, but cannot implement it because Japanese logistics lack capacity to transport massive quantities of standardized components. Reports describe American bulldozers moving more earth in hours than Japanese labor battalions move in days. Japanese officers understand mechanization, but cannot match it because Japanese industrial capacity cannot manufacture construction equipment in quantities sufficient for military operations while simultaneously producing tanks, aircraft, and weapons. Most critically, Japanese officers observe that American construction continues uninterrupted despite combat. On Guadalcanal, Japanese forces conduct nightly bombardments of Henderson Field specifically to disrupt runway construction. Despite inflicting casualties and damaging equipment, construction proceeds. Craters from overnight bombardment are filled by dawn. Damaged Marston mat sections are replaced within hours. The runway remains operational throughout. Japanese officers watching this through reports conclude that American construction capability exceeds Japanese capacity to destroy through artillery fire. This conclusion, devastating in its implications, means that even successful Japanese attacks cannot prevent American bases from becoming operational. Captain Yukio Seki, a Japanese engineer officer captured on Tinian, provides detailed testimony about Japanese perceptions in a December 1944 interrogation. His statements, preserved in declassified documents from Record Group 389, reveal Japanese understanding of American advantages. We knew American construction was faster than ours. We did not know it was this much faster. We thought they would need 3 months to make Tinian operational. They did it in 6 weeks. Our intelligence was not wrong. Our understanding was insufficient. American engineering is not better than Japanese engineering, but American organization and equipment make our engineering irrelevant. Seki continues. The prefabricated buildings surprised us most. We watched through binoculars from the southern hills. Buildings appeared overnight. We could not understand how. Later we learned they arrived complete from America, requiring only assembly. We build each building from local materials. This takes weeks. They assemble buildings in hours. When we realized this, we understood we could not compete. His testimony about Marston mat proves equally revealing. The steel runway matting was unknown to us. We saw photographs from reconnaissance flights showing runway surfaces that looked like metal. We thought these were photographs of temporary repairs. When we saw the actual matting after capture, we understood it was primary construction method. This changed everything. We required months to build coral runways. They required days to lay steel matting. The mathematics made victory impossible. Japanese logistics officers analyzing American supply operations reach similar conclusions. Major Takeshi Yamamoto, captured supply officer from the Tinian garrison, describes Japanese calculations in January 1945 interrogation. We estimated American forces would require 50 cargo ships monthly to support Tinian operations. Our submarines and aircraft would attack these ships. If we sank 10%, we would disrupt their supplies significantly. But American ships arrived by the hundreds. Even if we sank 20, another 80 completed their voyages. Our submarine force could not sink ships faster than America-built replacements. We faced industrial capacity beyond our ability to damage. The comparison of industrial output makes this clear. In 1944, Japan produces approximately 30,000 tons of merchant shipping monthly, while losing approximately 250,000 tons to American submarines and aircraft. Japanese merchant marine capacity decreases throughout the war despite new construction. Meanwhile, American shipyards produce Liberty ships at 1.5 million tons monthly. American merchant marine capacity increases throughout the war despite losses to German submarines and Japanese attacks. The mathematics doom Japanese strategy. They cannot interdict American supply lines when American construction replaces losses faster than Japanese forces inflict them. The construction technique innovations developed by Seabees establish practices that influence engineering for decades. The concept of parallel construction, building multiple components simultaneously rather than sequentially, becomes standard in modern project management. Critical path analysis, which Seabees employ intuitively through experience, becomes formalized methodology through operations research after the war. The use of standardized components manufactured centrally and assembled at remote sites influences everything from military logistics to commercial construction to disaster relief housing. The specific technical innovations merit detailed examination. The Marston mat interlocking system, using hooks and slots along panel edges, creates the template for modern modular runway systems. Current military AM2 matting employs essentially the same principle. Standardized panels that interlock quickly without specialized tools or skills. The flanged holes in Marston mat, which increase strength while reducing weight, demonstrate principles of material optimization that later inform aerospace engineering and automotive design. The concept of trading material efficiency for rapid assembly becomes fundamental in prefabricated construction across industries. Quonset hut design principles influence modern arch-supported structures. The self-supporting arch that requires no internal columns creates maximum usable interior space with minimum material. Modern prefabricated warehouses, airplane hangars, and storage facilities employ similar principles. The standardization of components allowing mass production with interchangeable parts becomes foundational to modern construction. The design concept of single-day assembly by small crews using simple tools influences modern disaster relief shelters and military temporary facilities deployed worldwide. The broader strategic implications reshape Pacific War dynamics. American offensive operations proceed through sequential island capture, followed by base development, followed by further offensive operations launched from newly developed bases. The speed of this cycle determines operational tempo. If base development requires 6 months, the offensive stalls for 6 months. If base development requires 6 weeks, the offensive maintains momentum. Seabee construction capability accelerates the cycle to its maximum sustainable speed. Islands are captured and made operational faster than Japanese forces can react. The Marianas campaign exemplifies this pattern. American forces land on Saipan on June 15, 1944. The island is declared secure on July 9th. The first operational airfield begins B-29 operations in October. American forces land on Tinian on July 24th. The island is declared secure on August 1st. B-29 operations begin in November. American forces land on Guam on July 21st. The island is declared secure on August 10th. Airfield construction begins immediately. By December 1944, 5 months after the initial Marianas landings, all 3 islands operate as major airbases, supporting hundreds of B-29s conducting strategic bombing of Japan. The Japanese have no capacity to match this operational tempo. The legacy of Seabee innovation extends far beyond World War II. The construction techniques developed under wartime pressure influence post-war industrial practice across multiple industries. Prefabrication becomes standard in construction, housing, and industrial facilities. The organizational principles of parallel production, simplified specifications, and rapid worker training become foundational concepts in operations management and industrial engineering. The use of standardized components manufactured centrally and assembled at remote locations influences everything from military logistics to commercial construction. The Quonset hut itself remains in use decades after the war. Many of the 170,000 wartime huts survive into the 21st century, repurposed as agricultural buildings, commercial warehouses, homes, and military storage. The basic design influences modern arch-supported structures used for warehouses, airplane hangars, and temporary shelters. The principles of self-supporting arch construction, standardized components, and tool-free assembly inform modern disaster relief housing and military temporary facilities. Marston mat influences runway construction worldwide, while pierced steel planking itself becomes obsolete with heavier jet aircraft. The concept of rapidly deployable modular runway surfaces continues. Modern military forces employ various forms of temporary runway matting descended from the World War II Marston mat. The AM2 matting used by American forces today represents the direct descendant of the original pierced steel planking. Recent operations restoring Tinian's Northfield runways employ modern matting technology whose basic principles remain unchanged from 1944. Laying modular sections that interlock to create operational runway surfaces quickly. The human legacy matters more than technological influence. The 325,000 men who served as Seabees during World War II represented American industrial capability mobilized for military purpose. They brought expertise from civilian construction, applied it under combat conditions, and created infrastructure that enabled victory. Their average age of 37 in the 1st Battalions meant they left established careers and families to serve. Many held positions of responsibility in civilian life: foremen, master tradesmen, small business owners. They accepted military discipline and lower pay than civilian work provided because they understood that American strategy required construction capability in forward areas. After the war, these men returned to civilian life, carrying lessons learned through Pacific construction under fire. They understood that impossible schedules become possible through proper organization and standardization. They knew that prefabrication eliminates bottlenecks in remote construction. They recognized that parallel production accelerates completion more than sequential perfection. These lessons, applied throughout post-war American construction, influenced the building boom that created modern American infrastructure. The Seabee motto, "Construimus, batuimus," we build, we fight, captures the dual nature of their mission. But the fighting remained secondary to building. Seabees fired their weapons when necessary, but measured success in runways completed, huts erected, ports constructed, bases operational. The fighting won territory. The building made territory valuable. Without Seabee construction, American offensive operations across the Pacific would have stalled repeatedly, waiting for bases to be developed using traditional methods that could not match operational requirements. The strategic bottom line remains stark. The United States built approximately 400 bases across the Pacific in 4 years. These bases supported the operations that defeated Japan. The bases required construction on a scale unprecedented in military history. The construction occurred in remote locations under combat conditions, using materials shipped thousands of miles. The construction speed exceeded anything Japanese forces could match or defend against. This construction capability represented industrial democracy applying its economic power to military necessity. In December 1944, Commodore Paul James Halloran, commanding the 6th Naval Construction Brigade on Tinian, stands on Northfield watching B-29s take off at 1-minute intervals for a major raid on Tokyo. The runway beneath his feet was jungle 6 months ago. The 269 B-29s, parked at Northfield, represent American industrial capacity made manifest. Each bomber required 165,000 pounds of aluminum, 1,460 pounds of copper, 4,000 pounds of rubber, and 11,000 man-hours to build. But these bombers are useless without the runways from which they launch, the fuel storage that supplies them, the ammunition magazines that arm them, the maintenance facilities that repair them, and the housing that shelters their crews. all of it built by Seabees in 45 days. Halloran watches another B-29 Thunder down the 8,500-foot runway, lifting off toward Japan. He thinks about the 15,000 Seabees under his command who made this moment possible. They are plumbers from Oklahoma, carpenters from Oregon, heavy equipment operators from Texas, electricians from Pennsylvania. They are fathers and grandfathers, many past 40, some past 50. They work 12-hour shifts in heat that exceeds 100 degrees. They sleep in tents when Quonset huts are not yet available. They eat K rations when regular supplies are delayed. They build under artillery fire when Japanese holdouts still operate. And they complete every runway on schedule. The last B-29 disappears toward the horizon. By morning, reconnaissance photographs will show which Japanese targets burned and which survived. More raids will follow. More bases will be built. American forces will continue advancing until Japan surrenders. And at every step, Seabees will transform captured territory into operational bases faster than the enemy thought possible. This is how America built 400 bases in 4 years. Not through superior individual soldiers, though American troops fought with courage and skill. Not through revolutionary weapons, though American technology provided advantages. But through the unglamorous work of construction, through the industrial capability to manufacture standardized components in quantities measured in millions, through the logistics to transport those components across oceans, and through the expertise to assemble them into operational infrastructure under combat conditions in timeframes that defied conventional engineering wisdom. The Seabees remain the forgotten heroes of the Pacific War. Histories focus on Marines storming beaches, carrier pilots winning battles, submarines sinking convoys, and bombers destroying cities. Histories rarely emphasize construction. Yet every marine assault depended on bases built by Seabees. Every carrier task force required forward ports constructed by Seabees. Every submarine operated from advanced bases developed by Seabees. Every bomber flew from runways laid by Seabees. Without construction capability, American offensive operations fail. Without Seabees, the Pacific War extends for years longer, costing hundreds of thousands of additional lives. The numbers tell the final story. Between 1942 and 1945, Seabees construct infrastructure equivalent to building 3 cities the size of 1945 San Francisco every year for 4 consecutive years. They pour foundations for 1.5 million personnel. They create operational capability across 6,000 miles of ocean. They transform the Pacific from Japanese-controlled territory into an American sphere of operation. And they accomplish this through expertise, innovation, and relentless work under conditions that would destroy lesser organizations. On Tinian today, the runways remain visible. Decades of jungle growth cannot completely obscure 8,500 feet of coral and Marston mat. The Quonset huts have mostly collapsed, but a few survive, rusted and weather-beaten, testament to engineering that prioritized function over longevity. Recent American military forces returned to Tinian, clearing vegetation and restoring Northfield for potential future operations. The new generation of engineers examining the World War II construction marvel at the speed of original construction. With modern equipment, contemporary engineers estimate they could match Seabee construction timelines, but not exceed them. The 45 days required to build Northfield in 1944 remains competitive with modern construction capability, employing equipment and techniques developed over subsequent decades. This reveals the ultimate truth about Seabee achievement. They built at the absolute limit of what industrial organization and construction expertise could accomplish. They wasted no time, accepted no delays, tolerated no excuses. They built because American strategy demanded construction, and they built faster, better, and more extensively than any military construction force before or since. The runway at Tinian stands as their monument silent testament to the men who transformed coral islands into the footprint of American power across the Pacific.